What's going on, everyone? My name is Johnny Bandon, and I will be your CCNA instructor for this CCNA series. In this CCNA video, we're going to go over routing protocols, which is part of our fifth section going over IP routing. So we learned in our intro to this section that the CCNA exam objectives only want you to know about two routing protocols, static routing and OSPF. So we could just, learn just OSPF and static routing, and we would probably be fine for the exam. But it would feel disingenuous as an instructor to not deep dive or give you a deeper understanding of routing protocols, how we categorize them, some of the original OG routing protocols like RIP, and all the information about routing protocols that you miss if you just stick with the CCNA exam objectives. So, what are routing protocols? So routing protocols are used to send and share information and pick the best routes to place in the routing table. So dynamic routing protocols, that's their whole purpose, right? They just need to share information with their neighbors and they need to place the best routes in the routing table. They do that with their algorithms, their different costs, different metrics, and administrative distances, right? Which we're going to break down. So we can see here in the second bullet, each routing protocol is going to have its own way to determine the best path to a destination. Because as we know, we don't just have one hop every which way to a destination, right? We could have multiple different hops. We could have multiple different ways we're learning about a route. So a routing protocol takes that administrative burden away from you and does its own algorithm, its own cost and path determination, right? Or it uses its own cost and metrics to determine the best path to a destination. So routing protocols are going to come in two major categories. That's IGP and EGP. So IGP, which stands for Interior Gateway Protocols, is for routing networks within an autonomous system. So what do we mean by that? So an IGP is typically used when you need to share networks within your own organization or your own domains. So let's say this right here is Capital One. So this is a large organization. It's going to have so many different headquarter buildings, big size offices, small little offices, right? And all of Capital One's network is probably going to be its own enterprise, right? So each one of these routers here, whether this one's in AZ and then this one's in Hawaii, New York, they're all going to need to share their local networks with each other within its own organization, its own autonomous system. So it does that by using an interior gateway protocol. And the reason we use that, an interior gateway protocol for internal routing, is because they offer fast convergence and easy configuration of routers within a network. And remember, the fast convergence, that's not subjective. That's what they're used for. But easy configuration, that may be depending who you ask, because IGPs can be plenty complicated as compared to EGPs. They both come with their own complications. Now let's get into EGPs. So exterior gateway protocols are used to route the internet, meaning they route between autonomous systems. So BGP, essentially the only exterior gateway protocol used today, it's called the Internet Protocol. Just in layman's terms, the Internet Routing Protocol. It's going to route networks between autonomous systems, meaning BGP is going to look at this group of routers as just one really network or domain, and it needs to tell this other autonomous system or domain about it. So let's say this is Citibank, and this is Capital One. And then somewhere in here, they're going to have connections to ISPs too. And then maybe those ISPs also have BGP connections. So you can kind of see how EGPs also have their own complications, right? We're not going to deep dive into BGP in the CCNA exam. This is all we're going to cover about it, what you're learning here. That BGP is used to route between autonomous systems. In the CCNP exam, you touch a little bit on BGP, but not like the old exams for CCNA and CCNP. And there's a reason for that. Remember, the CCNA is geared towards a network admin or engineer on the enterprise. On the enterprise network, you're mainly dealing with IGPs. And if you're dealing with the BGP connection, it's usually just one connection out to your ISP. Typically, we don't see these. Well, Capital One's a huge organization. You may be using BGP to share between maybe your West Coast and your East Coast networks, or maybe you divide it up in that sort of way, geographically, and you want to use BGP. But typically, we see that between ISPs, right? So on the data center or the service provider track of Cisco, that's when you really deep dive into BGP and go over like MPLS and the underlay and overlay and all the BGP metrics. We're not going to do that for the CCNA exam. We're going to focus on our IGPs. So within IGPs, we also categorize our routing protocols into two different major ones. So one category could be dynamic versus static, right? So we have dynamic routing protocols. And then we have static. Static is a routing protocol, okay? So a lot of people forget that, and it is an interior gateway routing protocol. But then within dynamic routing, we have another two major categories: link state and distance vector protocols. So distance vector and link state are terms to describe different dynamic routing protocols and how they share routes and build topologies and place routes into a global routing table. On the CCNA exam, we cover OSPF. That is a link state routing protocol. So you're going to get a lot of information on how a link state routing protocol works, especially when we go over OSPF. Whereas distance vector routing protocols are really old school. RIP is the only one still in use today, and I've personally used it engineering networks before. And distance vector can really be summarized as a per hop metric, meaning it determines the best path by how far away or how many hops a destination is. So you can quickly go over distance vector and why it's antiquated in a simple diagram, right? So we have these two connections here. Let's say all these ports are gigabit Ethernet, meaning 100 or 1,000 megabits per second speed. And then down here we have a T1 line, which is 1.544 megabits per second on both sides. If we implemented a distance vector routing protocol like RIP to get to this destination, let's say it's 1.1.0/24, which way is router 1 going to go? Well, this path down here is only 2 hops away, whereas this path is 3 hops away. So it believes that 2 hops is always better than a higher hop count of 3. So it's going to send traffic down the T1 line, even though this gig port is going to be better with better speed and bandwidth. So you kind of see how distance vector can be a little antiquated. Where I've seen it done on a live network, when I was in the military, one of the organizations I was a part of, they would have a hub and spoke topology for all their nodes, right? So we'd set up antennas to set up LANs, right, out in the middle of the field, and that antenna would give us reachability back to our hub somewhere in America, right? We'd be out in the field in North Carolina somewhere, and we get reachability all the way back to our hub, maybe in Florida. Well, our upstream or our like demarcation point for this router here would only be 1 hop away to this hub. And then that hub would route us out to our rest of our enterprise and internet. And we used RIP for that satellite uplink connections. Now, why? Because everything was just 1 hop away. So an easy way for us to learn about all of our other spokes that were connected to this hub was just RIP, a huge routing table full of RIP routes, because every single one was always just 1 hop away. So that's why I've seen it done in a live environment, and that's the only time I've seen it done. Okay, now let's jump in to link state routing protocols. So link state routing protocols are going to be OSPF and ISIS. So these protocols will share their entire link state databases within a routing area. So what do we mean by that? So a link state routing protocol, it cares about, I know it sounds crazy, the state of that link, meaning these links here between these routers. When we activate OSPF or configure OSPF or ISIS, it's going to take into account all the links, and it's going to start build its own link state database. And then its neighbor, once if it's established neighborship, it's going to send its link state database over to R1 and over to R3 over here. And it's going to take those link state advertisements and build a whole topology table, what we call the link state database of all known routes. And all these link state databases have to be synchronized. So with the link state routing protocol, we get full convergence, and we know about every single network and route out there on our enterprise because we all have the same link state databases. And once all those link state databases are synchronized, link state databases, then we have what we call full convergence, or our topology has converged. And now we can start sending traffic to all the known routes. And what OSPF or ISIS is going to do is run what's called its algorithm, or its shortest path first algorithm, on this link state database, and then place all those routes into the global routing table or routing information base. Okay? So the link state, right? So link state protocols will share what we call an LSA, which is called a link state advertisement, which is going to have all of its information and the information it learned from its neighbors. So once it starts flooding those LSAs out to all of its neighbors, it starts that link state database synchronization. Once that's done, we place the best routes in the routing table. So how do we determine the best path based off our link state database? We use a metric called the shortest path first, or an algorithm called the shortest path first, which uses bandwidth as the metric. So if we have a route from two different ways on our router, right? Let's say we learned about 172.16.0.0/24. We learned about it from R4 and R2, and R1 is trying to build its routing table. We're going to see the bandwidth, right, on each link to router 2 and router 4. And whichever has the best bandwidth is going to have what we call the lowest cost. And that's going to be the one placed into our routing table, or our next top, right? Okay, so we kind of just sped through the link state process, and really this is just a high-level overview. What I really want you to know about the link state is that there is a link state database that must be synchronized between all routers within an area. And we do that by sending LSAs, link state advertisements, right? And those LSAs are going to have plenty of different packet types we're going to get into: link state updates, request acknowledgements. And then I want you to know that once your link state database is fully converged and synchronized, then we run our shortest path first algorithm to place the best routes from our link state database into the routing table. And that algorithm is based off bandwidth. And we're just going to keep that at a high-level overview for now. Because when we go over OSPF, we're going to learn a lot about how a link state router protocol works. Because OSPF and ISIS, even though they're different, they're very similar in how they function. So when we deep dive into OSPF, if you ever have to learn ISIS, you're going to notice a lot of similarities. So now let's go over distance vector. So distance vector will use an algorithm that solely relies on hop count as the best metric or preferred path, which we went over. So there is a time to live, I guess, or a max hop count before something's considered invalid. and that's going to be a max of 16. We call that an infinite route. Okay. So distance vector routing protocols will send information to all neighbors, even if the information originated from that neighbor router. So what's the problem with that, right? Well, if we try advertising back out what we learned from R1, so R1, or let's say R3 sent us this, right? So R2 in our routing table, we say, okay, 172.16.0.1 was learned about from R3. Hey, R1, we know about the 172.16 network. R1 puts that into its routing table. It says, cool. And then it sends back R2 what it knows about, and it tells R2 about the 172.16.0 network. Okay. So now we know about it from two different ways. That could be a problem. And it's definitely a problem when we have a hub and spoke topology. So let's break that down. So I'm going to bring up my whiteboard here, okay? And this is an issue because of something called split horizon, or how we fix this issue is called split horizon. So let's say we have a topology that looks like this. Okay, this is R2, this is R3, this is R1. Right here, we have the 1.1.2.0/24 network. Right here, we have the 1.1.1.0/24 network. Okay. So let's say we're running something called DMVPN. This is our hub. And these spokes only know what the hub tells it. Cool. So R2 advertises the 1.1.1.0 network. Awesome. So the hub records that, puts it in its routing table as one hop away /24. And then it's going to also advertise, or it's going to know about 1.1.2.0, and it's one hop away. Awesome. Now R1's going to send what it knows about out both ways. So even the stuff that R3 sent it, it's going to send back out to R3, right? And do the same thing to R1. So then R3 gets it and says, okay, well, that's my connected route. So obviously I'm not going to place in my routing table what you told me about for 1.1.2.0, but I didn't know about 1.1.0, so that's pretty cool. And that's also just one hop away. So I have a pretty good metric for that. I'm going to tell you about that now, R1. So then R1 says, okay, well, now I'm going to advertise that out to R2 and tell it that it can reach this via R3. Well, R2 is going to be like, well, no, that's mine. But you're telling me it's also one hop away. So you kind of see the issue here, right? We're going to have something called like a routing loop. So how do we disable this? Well, what we do is enable what's called split horizon, which isn't going to allow you to advertise routes to your neighbor that you learned from the neighbor. So when R2 advertises its 1.1.0 route out, this hub will not send it back here. And what it actually does, depending what kind of split horizon you configured, is it's either just going to advertise a null, meaning don't worry about it, just drop traffic, right? When you get that routing update, or it's going to advertise to R2. It's going to advertise that /24 that it knows about, but put an infinite metric on there. So when R2 gets it, it just drops that routing update and says, I don't need to put that in my routing table. So split horizons definitely needed when you're in this kind of topology, right? A hub and spoke topology. Okay, so let's move on. Oh, I already had a nice diagram up there for it. That's what I get for working ahead of my slides. But cool, now we've learned about split horizon. And now let's go over EIGRP. So EIGRP is kind of an anomaly when it comes to the IGP category in which it fits into. So EIGRP is sometimes labeled as an advanced distance vector protocol, but really it's not distance vector at all, right? It doesn't use hop count as any way to determine the best path. It actually has a complex algorithm called the dual algorithm, diffuse update algorithm, and it's going to use K values to determine the metric of the best destination route. But it also doesn't create a link state database of all the networks that it knows about within an autonomous system or routing area, right? So ERGRP, one thing you need to know about it is that it uses bandwidth and delay as the two major metrics to determine how it sends traffic. Because in the CCNA exam, it may ask you, okay, what is the calculation for the metric on ERGRP? You need to know that it's bandwidth and delay. So ERGRP does do the basic things that all routing protocols do. It creates neighbors in its neighbor table. It's going to create a topology table similar to the link state database of OSPF. And then it's going to execute its algorithm on that topology table and place the best routes or paths to a destination route into the routing table. Okay, now for the last thing we go over in this video before we take a break, because I don't want this going too long, is routing protocol characteristics. So every routing protocol has similarities. Every routing protocol has its own hello packets where it's going to send out its enabled interfaces and create and discover neighbors and create a neighbor table. Each routing protocol has a multicast address that it uses to send out these hello packets. Every routing protocol has hello packets, right? Every routing protocol also has its own parameters that have to match to be able to become neighbors with other routing protocol enabled routers. Each routing protocol also has its own algorithm and its own administrative distance. We're going to learn about administrative distances in the next slide. This is how well a router trusts a routing protocol. So an administrative distance goes into the best path determination when a router receives the same destination route from multiple neighbors running different routing protocols. The administrative distance will help determine which one is to be more trusted, okay? So the lower the administrative distance, the better the routing protocol is considered. So in this next slide, we see this chart of all the characteristics of all the major routing protocols. And we're just going to stick with these three right here because this is what you may see on the exam, okay? So they each have their own metric. With RIP, it's distance vector, and it goes by hop count. With the ERGRP, we use bandwidth and delay to determine the best path. That's our metric. With the OSPF, we just use cost. RIP and ERGRP are going to send routing updates every 30 seconds, meaning we're sending the full routing table every 30 seconds. OSPF only does that every 30 minutes because OSPF only sends changes when there's only sends routing updates or LSAs when there's been a change in the network, and it'll only send a 30-minute advertisement, right? Not the entire routing table to ensure its neighbors are still up. And that's different from the hello and hold timers. And then we see each routing protocol has a multicast address assigned to it that's going to send out its hello packets and its own routing protocol packets. So RIP's going to use 224.0.0.9. And remember, this is a class D multicast address. ERGRP uses .10. And then we see OSPF has two different ones. And this is when we have a broadcast OSPF network, which we're going to learn about. And you have a designated router and a backup designated router. And we're going to get into that. And then we have administrative distances, which you have to memorize. RIP is the worst one out of all of our IGP protocols here, is 120. ERGRP, we have two here. And we're not going to get into what an external route is, but that's when ERGRP is redistributing from other routing protocols. Its administrative distance is 170. Its internal or just regular administrative distance is 90. Then OSPF is 110. So if all things are same and your router is learning a route from RIP, ERGRP, and OSPF, and the prefix length is the same, it chooses ERGRP as the routing protocol to place in the routing table because it has the best administrative distance or the lowest. The only other IGP that beats ERGRP is static, and static routing protocols have an AD of 1. All right, awesome. So please, take a second to look over this, put in your notes. The important things to know is definitely that administrative distance and what their metric is on both of or all three of those interior gateway protocols. Okay, now we're going to pause the video here, and our last video is going to go over how does a router choose to put routes into the global routing table. And we're going to go the routing table goes off these 3 rules. And we're going to dive into this in our next section. So stay tuned and thank you.